So we're going to have our last speaker, Professor Christian
Kuehn.
Kuehn. Thank you very much. So Professor Kuehn is a full professor at the Technical University of Munich. His research lies at the interface of differential equations, dynamic systems, and mathematical modeling. He's an associate editor in SciAm Journal of Applied Dynamic Systems and Journal of Nonlinear Science and other journals. So today, Professor Kuehn will talk about dynamic on deep neural network. Thank you very much for coming.
Thanks very much. So it's my first time here. Thank you very much for the organizers for inviting me. So my background is actually quite interdisciplinary. I'm currently in the math department, but I actually studied math, physics, computer science, neuroscience, and mechanical engineering. So common across all those fields in some sense is nonlinear dynamics, which is sort of my love in science, so to say, that I want to explain how nonlinear systems work, and deep neural networks are one particularly interesting class of nonlinear systems. And I would like to know how they work. So first of all, I want to view them as dynamical systems, which is sort of clear. You propagate information on a network, but you also learn, which is also a dynamical process. So this is just a very brief introduction I will be giving. And then I will sort of, since I didn't know what audience to expect, so to say, because I don't know many of you, I will sort of delve into a few results, and I will try to focus on this B topic, network structure and norm performance, because it's maybe the most accessible for a beginner, so to say. And yeah, so let's get to it. So first of all, the question that we would like to ask is somehow, why do these AI methods work? So I'm more on the end of, I trust the applied people in engineering and so on to make things optimal in practice, but I would love to know why things actually work and what the basic principles are and how we can improve those basic principles to somehow get better neural networks, get better systems from the ground up, so to say. And I view them as dynamical systems, and so a little bit of notation. I will talk about graphs and particularly adjacency matrices. And yeah, there's always noise. That's always a good thing. That's why I have the professorship for multiscale and stochastic dynamics. It's always very good to say there is always noise. So this is very nice. So this is basic notation. So mostly I will talk about networks, and this is sort of quite standard. But so there are two processes, in my view, on deep neural networks that are interesting or important. One is, if you're given the deep neural network, how does propagation sort of information across this neural network work? And the second process is, how do you learn the sort of weights? I will focus on the first process, how you actually sort of propagate information today. You could do the same thing, and we are working also on learning dynamics and coupling the two, if you so wish. But okay, to keep it simpler, I thought I will do this. And first, I want to distinguish between sort of classical things that somehow are predating machine learning and artificial intelligence. So propagation on a network is actually quite a classical topic. So I've put up an equation here, which is sort of a typical network equation where you have nodes xj, they have intrinsic dynamics fj, and there's coupling, meaning inputs from other nodes, and it's coupled on a graph that's given by an adjacency matrix ajk, and n is the number of nodes. And then there's, of course, learning dynamics, which would mean, how do you find these network weights for the nodes? Okay, fine. So there's dynamics on the network, which I will focus on today, which you can think of as a sort of direct analog to what in physics or statistical mechanics you would call interacting particle dynamics, that has been around for donkey's years. And there's dynamics of the network, which is basically optimization algorithm dynamics. And if you combine this, you have what's called in network science actually adaptive or co-evolutionary dynamics, or you can view it as a control system or whatever you like, but in the end, it's basically a coupled sort of thing of the two. And today I will focus on the first one, so on dynamics on networks, not off networks. Okay? Good. So first topic, why is there sort of a deep link between the sort of more computer sciencey discrete structures and dynamical systems and differential equations? I put up a differential equation in the beginning. Let me briefly at least say why you can link the two. This is actually very important. So for example, let's, for illustration, just consider this dynamic system on a graph, which is just an ordinary differential equation with intrinsic dynamics. Let's suppose it's all the same. Every node has the same intrinsic dynamics. They are coupled, and they're all coupled by the same coupling function. And what you would want, and what you could want, is a probability distribution that describes the typical particle, u, at position x and time t. And you can prove that the typical particle, actually in the classical sense without a graph, satisfies such a mean field PDE. So this is just the probability distribution of a typical particle that satisfies this mean field so-called Vlasov equation. If you put noise on the first equation, you get a Vlasov-Fokker-Planck equation, and so on and so forth. Okay? But now, an interesting point is what happens if you have graphs, or hypergraphs actually. It's no problem doing hypergraphs as well. Here I only talk about graphs. If you make a bigger tensor, I can put bigger tensors in my theory, that's okay. Okay? So the interesting viewpoint that we discovered a few years ago is that if you want to take sort of a neural network or some sort of more graph theoretical dynamical systems to its limit and link it to a differential equation, you have to take the limit n tending to infinity, the number of particles tending to infinity. And if you do that with the graph, you need to make sense of the graph limit itself. Because you're on a graph, not only are the dynamics on that graph having to be taken to the limit, but actually the graph itself also has to be taken to the limit. Maybe you are familiar with something called graphons. That's something that many people know as graph limits. We generalized this and put in something called graph ops, graph operators, which are actually measure theoretic limits that can capture much wider graphs. And what we have is basically a limiting theory that says we can derive a Vlasov mean field PDE. I won't go into the details. That somehow tells you can indeed go from this discrete system either in discrete time or continuous time to a mean field limiting object, either in the continuum or this mesoscopic mean field sense. And these graph ops are in some sense more general ways of representing graph limits. Okay? Good. And here's the formulas for this. Is basically a big sort of convolution type integral as you would expect. That convolution type integrals should appear because roughly speaking, the heterogeneity of the graph in the limit of this dynamical system gets sort of convolved with the rest of the dynamics, if you so wish. Could go back to Amari and Wilson Cowan in the 70s in neuroscience if you so wanted to. Okay, so we have lots of results on this. I just collected them here. So we can basically really take limits of all sorts of network dynamics. And we can also do it now in the end on sort of co-evolutionary things when you have sort of optimization dynamics of the weights. We can do it on hypergraphs for certain restricted hypergraphs and so on. And this started several years ago when I had a bit of time during COVID to somehow look at graph ops in a bit more detail. So in some sense, this first paper, I was like, okay, I'm at home. I've COVID myself. I'm really sick. What do I do? So let's try to write a paper. And that came out of this, so it's quite nice. So it's a very active field. I won't go into this detail. Lots of people working on it. So the idea is that there's this duality. You can always go in some sense from a network dynamical system to a differential equation if you wanted to in various ways. And now we can do it in very much generality because we can allow very general graph structures as limits. And the mathematical results are quite detailed and rigorous, and you can show existence, uniqueness, regularity, dynamical approximation, etc., with all these methods, and it's now robust theory, I would say, after a few years. There are still lots of open questions. Actually, for hypergraphs, some questions are still open, so if people are good at this, they can give it a go. Yes? Specific example for... You mean specific example of the dynamics of such a system, or? Yes, sure. Let's do a specific. Should we? I will challenge you back. Let's do a specific example together, shall we? So let's do the following. In Germany, we have this tradition, as you very well know, of knocking after a talk. Do we agree that this is a tradition? So let's everybody do this tradition of knocking, and not very loudly. Okay, and try to synchronize while knocking, not very loudly. And now try to knock a little louder and then try to synchronize. Yeah, I want just you do it. Louder. Try to synchronize. See, that worked much better. So basically you can think of you as being an oscillator. You're having a phase, right? That you're doing with the knocking, that's the xj. The f of xj is basically your intrinsic frequency, the way you would knock without anybody. The other stuff, the g, would be an interaction that tells you, like more like a first term of a Fourier series, like a sine, that tells you who you should synchronize with. And there's a coupling, which is this sort of mean field of the sum of the people that you hear knocking. And then what you have sort of enacted is sort of a transition or a phase transition of when there's not very much coupling K, you cannot synchronize, and when there's a lot of coupling K, you can synchronize. Is that concrete enough? Yes?
Most things in
Yes?
what you're describing is
Yes, you can make it stochastic.
an extension of
Yes.
the
Yes, you can do that. So you can first put noise on this guy here. So you can put noise here and you get a Vlasov-Fokker-Planck equation, so a diffusion term in it. And you can even get an SPDE out if you wish so, by taking the first correction to the fluctuations into account, so making basically a system size expansion, and then this whole thing becomes an SPDE. Yes? Well, I mean, in some sense, if you put in reasonable noises where people know the behavior of large numbers of noises, where some form of a generalized central limit theorem is okay, then you can do it. If there is some weird noise that doesn't satisfy any sort of central limit theorems, then no. But that's expected, right? Because if there's something that doesn't satisfy any good properties, if many noise processes interact, then you cannot get any macroscopic limit out. Whereas as long as if you can get something like a good central limit theorem type result out for the noises that you're having or assuming, then yes, you can get a mean field out.
Yeah, most
That works.
and for that there is a
Yes.
central limit.
Yes.
But when things are not see that.
I mean, if it's not Poisson, I'm not an expert on it, but there are people working on it like Daniel Lacker at Columbia and Kavita Ramanan at Brown. They do this and they can put all sorts of jump type processes that are even more complicated on it and they get mean field limits. I'm not an expert, but they claim it's pretty general already. So if you talk to Daniel or Kavita, they will tell you. Okay. So very good. So that was the brief first topic. Let me go into a second topic, which is sort of maybe I will spend a little bit more time on it because I can concretely go through a calculation. The previous topic, I cannot do that. So here the goal is slightly different. So what we are wanting to do is we want to understand actually a bit of geometry. So the idea is, given a neural network, whether it's a form of a normal feed-forward neural network or the direct analog of the continuum limit of this, which is a neural ODE, as you well know. So we want to understand, depending upon the architecture of this network, whether it has augmentation, meaning initial and last layers, whether it has bottlenecks and stuff, what geometric functions, so what geometry does that network represent? So this is actually quite a, I think, cool problem because it says, given a neural network and the function representation it can represent, what type of class of functions can you actually represent with it? Yes? So what we will do is we will have as a central object of study Morse functions. If people are in geometry, I hope you know what Morse functions are. Well, basically functions with non-degenerate critical points. So x to x squared is a Morse function. X to x cubed is not a Morse function because it has a degenerate critical point at the origin. So the question is, when can neural networks actually approximate Morse functions? Fair enough. That's a fair question. So how do you do this? So let's do standard feed-forward neural networks. So this is the normal update rule, several layers, and you have a matrix WL, and then bias is BL, or just a shift by a vector, and you have an activation function sigma L. Okay, you can also put additional sort of weights and biases outside, or you can do both. But nevertheless, you're upgrading from layer to layer your neural network, and the whole sort of thing is the question, what function does it represent from input to output? And the question is, when is it a Morse function? So when does it have geometry, and when does it have sort of more degenerate geometry? When is it not a Morse function? Okay, this is just notation. I want to compactify the notation. I write it like this. And then there's basically a scalar map from the input to the output. Yeah? So you have some input and some output, and you're asking the question, what type of sort of map is that scalar map? And I will make the assumption that the activation function is monotone. Well, you can make it a little bit sort of more degenerate, but for simplicity. And then the notation will be that I have these sort of updates, and then I have my next level update and so on. And this is the same notation, just that I compactify everything again with sort of H and S0 being G0 and so on. So it's basically just a big feed-forward neural network that you're all used to. Okay? And the question is, when is it Morse? Okay? When is it geometric, so to say? So first, easy lemma with my PhD student Sarah Viola. So this is an easy lemma you can do yourself. It's from the 50s or whatever. It's just in the paper there where we did it. So except for measure 0 set, matrices have full rank. That's pretty obvious if you think about it. So if you pick a random matrix, it has full rank. So this is a little bit less obvious. So this is what we wanted to prove. It's because it's an analog to the theory of normal forms in dynamical systems. It says that you can somehow take your arbitrary feed-forward neural network and you can compactify it, put it into a normal form so that you only have full rank weight matrices. Meaning if there are some sort of rank deficiencies, you can give an equivalent representation of a neural network with only full rank matrices. Which is sort of nice because it tells you this is the minimal thing or normal form in the dynamical systems language of that network. It's a little bit like if you would Taylor expand a function and it is singular and you all throw away all the Taylor expansion coefficients that you can transform away by coordinate changes, then that would be called a normal form in dynamical systems. And we are applying this normal form theory now to neural networks in some sense with a few twists. Okay? So here's the idea that you can do it. So here's an example with weights and everything. And you see here that if you look at W2 and you look at the third column, then this is actually a linear combination of the first column and the second column. So if you look at all the weights here, you can check that this 2, 2, 1, this is this guy, can be given as 2 times the first column, which is this node here, which is 1, 1 times 2. Plus 1 times the second column, which is this guy, which is 2 and minus 1. And if you add these two up with these weights that I mentioned, you indeed get 2, 2, 1. You can do that in your head if you like to. Okay? So there's a linear dependence, so a rank deficiency in that matrix, because the columns are dependent. So now you can compactify it, and this is the compactified version or the normal form version where I took away that node, and this is the network that you can show explicitly is actually equivalent to the previous network as a function in the feed-forward structure. Okay, so I've just sort of removed this dependency. And then I find one more dependency. So this guy in the first matrix here, the W tilde, is again just a multiple of the other guy, which is pretty easy to see. Yeah, 1, 2, and 2, 4 is 2 times a multiple of this. And again, can compactify this away. Yeah, and then there I find another one, which is over here. And I can again get rid of this and change the weights. And now you have actually a network that has full rank for every matrix. And we can prove by a longer argument that indeed this is always possible. Yeah? So this is like a normal form of a feed-forward neural network, sort of the minimal one that you need to represent everything. And that's full rank. And because full rank is good, we want full rank, and I will show you later why. Good. So I found a normal form for these things. Now I have to explain what I mean by architecture. So this is what's called a non-augmented neural network, where basically you should think, this is our definition, that somehow the layers are always decreasing in size. Okay, fine. Then there's an augmented neural network where you actually allow increase and decrease. So by definition, you allow the layers to increase in size and decrease in size. And then you have something with a bottleneck where you somehow allow also something in the middle where it's decreasing and then increasing in the middle of the neural network. Okay? And the question is, what does that entail for the geometry of the function that I want to represent via this neural network? So you do that, and you have the same thing as an analogy. As I said, you can always think from the discrete to the continuous. In the continuous, if you take the limit of a feed-forward neural network, you will actually figure out that this would be a way to do it. If you have skip connections like this, then indeed you find out that the neural ODE is the limit of these feed-forward neural networks. That's quite classical. And then the weights basically become this non-autonomous driving. This is also well known that the weights can be converted to non-autonomous driving because time is basically in which layer you are. And since you have put weights everywhere, now this becomes non-autonomous driving. Okay? So this is quite classical by now. Okay, good. And we add 2 linear layers, one in the beginning and one in the end. And then you can again have the same thing, non-augmented neural ODEs. On the ODE level would be things that only go down in layer size. Yeah, augmented would be on both sides. You can go up and down at the end. And you have bottlenecks, which actually at the beginning or at the end, you have a singular matrix. Okay, so you can have the same concept that you had for discrete networks on the continuum limit of ODEs. So now, this is the formal definition of a Morse function. If you haven't seen it, it's a function without degenerate critical points. So you take a point of that function, which you currently think is the stuff that your neural network is representing, and you want to know whether that point that you have is singular or non-singular if it's a critical point. Okay, this is very important because in some sense this is just a rewritten of an old result from the 50s. Morse functions are actually dense in smooth functions. That's actually not so surprising if you think about something like, x cubed. It's not a Morse function, but you can make a Morse function that's arbitrarily close to x cubed, but just near the little zero, you have a little bit of a bump. You put it in and then it's Morse. Because if you have two little bumps in this sort of function near zero, then you have two non-degenerate critical points and it becomes a Morse function. Pretty easy. Okay, so now we want to subdivide the space. So the idea is we want to find which neural networks and which architectures can represent which types of Morse functions. So the ones without critical points, these are trivial. We call them C1 because, okay, these are all functions that have no critical points, whatever. Then you have functions with critical points, but they are Morse, meaning that the Hessian is non-degenerate. And then there are points where they're non-Morse functions, meaning the Hessian is singular. And you can subdivide the space into sort of direct sort of union in some sense of all these functions, which is fine. So now the question is which architecture, I put the architecture over here, and this is the feed-forward discrete case, and this is the neural ODE case. Which types of functions do these represent? So, okay, first assumptions, I will have normal forms, so all weight matrices have full rank. I can always do this by my first theorem. And I will always assume that the vector field of the ODE is sufficiently regular, and then you can actually show that, for gradient, the gradient of a feed-forward neural network is this. And then you can actually show if it's non-augmented, it cannot have any critical points. So you don't have Morse functions in that case. Because you can calculate, actually by a chain rule type argument that's quite long, but you can show that everything is basically Morse. This is something that first was proved by Kurochkin that we refined in a more general setting. So for neural ODEs, you can do the same thing. You can look at the gradient, which is you need to check the gradient to check whether you are Morse. And then you can show that you always have full rank also for a neural ODE case, meaning if you have this sort of setting of a non-augmented neural ODE, you always have full rank. Okay, for non-augmented neural ODEs, always Morse. So you can put it in here that non-augmented systems structurally, meaning this is the network science viewpoint, structure implies function. In this case, structure implies geometry of the underlying mapping is a Morse function because it's non-degenerate. Okay, so regularity of critical points, we need some lemmas that tell us when are the critical points non-degenerate, and we view the network weights and biases as parameters. And then we need to check whether certain derivatives are actually non-degenerate because we want to check whether the Hessian is non-degenerate, right? That's what we want to check. And indeed, there is a lemma from Niculescu that tells you under certain generic conditions, you can actually show that if you have certain matrices that have full rank and you check that they have full rank, then indeed you have a Morse function. Okay? And we want to apply this lemma. Basically, we have to calculate derivatives. Okay? So you have to determine the rank of a certain matrix, and we need to take parametric derivatives, which are derivatives with respect to the weights and biases. And that gives you in the end whether you are Morse or not. Okay? So for an augmented, now this is with the augmented layer, so you can grow and decay in the beginning or end, you can actually show that you almost everywhere have full rank of all these matrices for the discrete and the continuous case. So it's true for the discrete feed-forward neural network and for the neural ODEs, meaning you can calculate and prove that the gradients have a nice structure, namely they have sort of stacked structure that you can exploit in the proof. And once you exploit that stacked structure, you indeed find this result, except for a Lebesgue measure zero set in weight space, you either have a C1 or C2 case for both of these when you're augmented. Meaning if you have an augmented layer, you can get Morse functions. Meaning, and you can also get non-degenerate critical points. Roughly speaking, meaning if you wanted something that had minima and maxima that are Morse non-degenerate, you need augmentation in your neural networks. So to get geometry of Morse functions, that's basically what the augmented layers in your neural network do. We never noticed it like this, but that's what they're doing. Okay? Yes? Yes, I mean the Morse function basically, if you have the neural network is just a function. Okay? And you want... I want to show whether these neural networks under what structural assumptions they can represent Morse functions or not. Meaning every neural network is just an input-output mapping. Morse functions, why? Because they are the most natural geometric building blocks in dynamics, because you know that if you have a smooth function, almost every smooth function is Morse, and it gives you the shape geometry of smooth functions locally, meaning you want to know whether a neural network is able to give you local non-degenerate critical points as a shape, as an input-output mapping. So you want to link, in some sense, the underlying geometry of the neural network to the property of what type of geometry it can represent. Okay? Yes, of course, because we know which type of discrete augmentations you need to really represent a Morse function, which types of augmentations are not possible to represent a Morse function. Well, you could try it harder, sort of you could get finer information topologically. We haven't done that yet, but you could try. You could try, because in some sense, Morse functions, as you know, are at the sort of core of Morse bot homology and so on. And you would love to do that, of course. This is sort of the kindergarten version of this long-term research program. But okay, you have to start with the kindergarten. I mean, what can you, I mean, like, maybe you're all bright and you jumped over kindergarten and went to high school immediately. But I didn't, so yeah. Okay, so basically meaning if you have augmentation, so initial and final layers, you can get Morse functions. And for bottlenecks, let me briefly go through this. For bottlenecks, it's actually possible that you can have also functions that are not Morse. Meaning that if you have these bottlenecks in your feed-forward network, it's actually possible to get degenerate critical points. So roughly speaking, if you want to represent degenerate functions, put bottlenecks in. Okay? That's a very nice and neat and simple rule, so to say. And we can prove that, of course, yeah? And everything sort of fits together, and there's a direct analogy between the discrete case and the continuous limit neural ODE case. Okay? Good, so this is very nice. So let me get back to something. Do I have a few more minutes? Or how much time do I have left? Probably. Yeah. Very good. So what I did now is basically told you that there's a way to simplify neural networks, get a normal form for them, and then depending on how they are structured, whether there's augmentation layers in the beginning or end, it tells you whether the function can represent this geometric object called a Morse function or not. But then you might be wondering, in some sense, is there other information that you could gain from dynamical systems and that you could sort of figure out from this viewpoint as a dynamical systems or neural ODE or mapping viewpoint that tells you something about approximation for neural networks? We also did that, and we had this very nice sort of idea to say, okay, let's do not the universal approximation theorem that you're all familiar with. I guess most of you are familiar with the universal approximation theorem, yeah? So let's don't do that, because in some sense it dilutes our view, at least in my view. I mean, maybe not your view, but in my view. The universal approximation theorem says that if you have a neural network and you sort of make it big enough, then you can approximate any function, roughly, yeah? Something like this. But in a way, it's a bit, you know, you can do it easier, I think. So you can first ask, why can you represent functions at all? And why is it important to have that the neural network is big? Okay? And how simple can you get and how easy can you prove this? And if you take a geometric view, the proof is actually, as I will show you, 3 lines. By the way, even the original universal approximation theorem is probably more like Sharkovsky theorem reloaded from the 60s, but that's another matter. But okay, so the universal embedding problem doesn't ask for approximation, it asks for on-the-nose representation. Meaning, you have a neural network, you want it to represent a function, and the question is, can it represent that function exactly? If it does, I will say it universally embeds. Meaning that if I give it a class of functions and then the neural network can represent all of these, then the universal embedding problem is solved. And the question is how much and how big does my neural network have to be to allow for this sort of embedding problem and not the approximation problem. Okay. And for the neural ODE case, the nice thing is if you have neural ODEs, remember that for neural ODEs, the idea is you take an input initial data, you flow it forward, and you get an output initial data at a certain time t. And the flow map from time 0 to time t is your input-output map for your neural ODE. Yeah? So this is the mapping, the function that the neural ODE represents. So then the question is, can I find a vector field or a flow that exactly represents any given mapping that should go from input time 0 to final time t? Is that possible, yes or no? And actually the proof is pretty easy. So let me do the proof. You only need two classical geometric theorems. So I thought people in geometry would like this. So if you're given a mapping, any homeomorphism actually, a mapping from some space to another one, there's something called the mapping torus, and there's a suspension flow theorem. So the mapping torus is nothing else. You take your mapping that goes from x to phi of x, and then you basically glue what you get after phi of x to the stuff that you started with at x. So the gluing has to be that x gets identified to phi of x, which is this equivalence relation down here. And then the mapping torus is just a stretching over a certain time from 0 to t that says there's one sort of space and another space, you glue them together and you get a torus. Okay? This mapping torus quite classically says that if you have any sort of ODE and you have any sort of given diffeomorphism, then you can always find an ODE that has this diffeomorphism as a time t map. Meaning, okay, I'm giving you a map from x to x, and then I say the way I embed this into an ordinary differential equation is this idea of the mapping torus. I just write out this very simple ordinary differential equation, and you can show that if you do this geometric construction of taking this ODE, flowing it forward for time t, and then applying the mapping torus, then you see that indeed this time t map of this precise ordinary differential equation precisely is the given diffeomorphism. So this means that by this suspension flow theorem, you can sort of connect every sort of discrete mapping to a flow of an ODE. Yes. Okay? So there's always this possibility to do this. Well, and now it's easy, right? If you're given any diffeomorphism, you can always represent this by a neural ODE. Why? Because, well, you just take your diffeomorphism, you make the dimension big enough, so you basically take the mapping torus that you have, that you want, take that mapping torus, embed it into Euclidean space by Whitney's theorem, and then there you have your representation of your mapping by a neural ODE exactly on the nose by the suspension flow plus Whitney. So it's a two-line argument in classical geometry that every sort of given diffeomorphism can be represented by a neural ODE if the dimension is large enough, and the large enough dimension is basically you need to embed the mapping torus in a sufficiently large space. That's really all there is to it. That's basically the two-liner why neural networks work. There's not much more to it, really. Yeah? Big dimension follows from mapping torus needs to be embedded in something big. That's it. Okay, good. There's also the problem sometimes if you restrict the dimension and you try to do Whitney with less dimensions, it doesn't work. So there's a geometric restriction that if the dimension is not big enough, it might not work. Well, you know that from universal approximation. There are counterexamples in some sense. So this is the easy form of understanding universal approximation. You just take your neural ODE, you just embed it with the mapping torus, done. Okay, good. I don't have much time, so I will probably skip the last topic in the interest of having more questions. But you might wonder, okay, at some point, all these methods of pen and paper analysis and trying to figure out why neural networks work will run out. Of course they will. Let's be honest here, yeah, I'm not delusional. I mean, I've studied other subjects beyond math. I know that eventually they will run out. But how could you ensure that you still have working proof of certain complex dynamics in a certain neural network? Would it be possible to give a rigorous mathematical proof that a certain neural network produces, say, hallucination, or that it is susceptible to adversarial attacks? Could you give a rigorous proof of that? In general, the answer by pen and paper will usually be no. Right? You have to make too many assumptions to make it practical. So there's this big gap between practicality and theoretical provability that we are all aware of in neural networks. And what we are proposing here in this last topic is to bridge that gap by automated proofs. So the idea is that the computer proves that the machine learning does something. This sounds weird, but I think it's the only way forward if you want to bridge that gap. So we're using computer-assisted proofs to, for example, show that a neural network has lots of periodic orbits and potentially could be chaotic, for example. And this cannot be verified by hand, but we can do it with computer-assisted proof to show that indeed there are lots of periodic orbits and that indeed the neural network could be potentially chaotic. So this is joint work with one of my postdocs, now actually professor in France, Elena Quairolo. She will go to Rennes very soon, probably in a couple of days. And so the idea is neural networks are finite sized but large. They are highly nonlinear. they're computational objects, and our idea is to use rigorous computer-assisted proof to show that they have complicated dynamics. And what we have shown so far is that indeed certain types of simple neural networks like this, these guys over here, we have shown that under certain assumptions, I won't go over them in detail, so when you vary parameters, that indeed you can show that they have lots of periodic orbits. We do this with a computer-assisted Newton-Kantorovich trick. I can go into this if you want to. But we can show that indeed we can validate 200 bifurcations rigorously, and we can show that there are over 200 unstable periodic orbits in a given neural network, meaning it's basically chaotic. So meaning this is a way to bridge the practical gap where people use something in practice with data to the ultra theory gap that I started from, that you can indeed put these computer-assisted proofs in the middle that tell you when you can actually show something rigorously about the complexity of the network representation, which is sort of rather neat, I think. It's a neat idea. Okay, so the summary, hopefully I have 1 minute for the summary, if the chairman allows me. Very good. Nice chairman, I really very appreciate it. Pay you later. Okay, so the summary is, my view is it's quite good and helpful to think of neural networks dynamically. Because if you do that, you can harness and harvest a lot of understanding about nonlinear systems that we have garnered over the last hundreds of years. I mean, and what we try to do is first show that there is indeed a lot of similarity between continuous time and discrete time systems, that you can get many limiting systems that you can analyze with pencil and paper out of infinite node limits and deep networks. We also shown that the structure of the underlying network implies geometric functioning of the network by this Morse function argument. We have shown that if you want to have simple results in neural networks, they can get even simpler if you apply a geometric insight from dynamics, like universal embedding versus universal approximation. And lastly, we proposed the bridge to go from practical to theoretical by using a computer to assist proofs for dynamical systems as neural networks that are actually not tractable by pen and paper. And so for more information, please go to my website that tries to be easy to remember by its name, hopefully. And then thank you very much for your kind attention.
Thank you very much for the talk. Any questions?
Yes, then you cannot have universal embedding in certain classes if the function you are having as an activation function is too degenerate, but it's arbitrarily close to something that's monotone and smooth, right? If you have a ReLU, I can find a smooth function that is arbitrarily smooth and is arbitrarily close and most reasonable topologies to a ReLU function. So I could universally embed something that's arbitrarily close to a ReLU, but not the ReLU itself because it's degenerate, because it has points where it's actually not smooth. But that's okay. I mean, in the end, you don't expect with pencil and papers to have sort of, how to say, the sharp results on any sort of structural degeneracy. And you would need to treat things like piecewise things again separately, because like smooth dynamics and piecewise smooth dynamics are two different fields, really. So there are different methods. But if you're an expert in non-smooth dynamics, maybe most of you are not, but there is a technique called sort of Filipov regularization and non-smooth blowup, where you can actually turn something like a ReLU into a smooth object on an arbitrary microscopic scale. This is well known in dynamics, and I'm sure ML people will discover this soon. I'm pretty confident. They will. I don't know how they will call it. That's a bet that's open, but okay. Yes. I think you were first. So absolutely right. There's another side that I haven't talked about at all, fully admissively. I am sort of more interested in the basic science. There's the data side of things. If you have limited data, how much can you get with limited data? How good is the approximation with limited data? And my argument is always like, in a way, if you think back in physics, right, you could say many of the physical systems that we're having are idealized. In some sense, think of, for example, classical Navier-Stokes. It describes an ideal fluid. But it's not really in reality always an ideal fluid. There's temperature fluctuation, there's all sorts of external forces, and Navier-Stokes is never correct. But the insight we gain from Navier-Stokes is still useful because it tells us about the basic flow patterns that fluids can have. So this is in some sense the way I would see this. I'm not going to tune and do something practical with data, but I'm trying to provide basic insights why certain methods might work and what the underlying principles are. So it's more basic research than data research. You're right. No, I mean, that's the point. That's why we are doing this theory in the beginning, right? So if you think so, this theory indeed has also adaptive general networks that can be degenerate and they don't have full rank. And we are only at the stage, sort of stage 0 here, where we can actually link the discrete and the continuous worlds to get the right limiting equations. But of course, if these are then more complicated, meaning they could be more degenerate than just simple feed-forward neural networks, as you say they could be, then the question is, what types of analysis, based upon now the analogy of having a discrete system and its continuum limit, can you do like in my second part? And that so far hasn't been done, and it's sort of an open question, because it basically says that if you have a sort of general PDE flow, for example, that maybe is even adaptive, meaning coupled to the learning, what is sort of the actual geometry of the input-output map of the resulting infinite-dimensional PDE? Nobody really knows. I mean, you can do in practice, of course, things that tell you what to do, but in theory, it's very hard, of course, to prove what really these things then do.
I agree.
But there are lots of people working on it.
The
I mean,
entire thing, your forward process is coupled to your parameter. You have to think of stability.
yes,
Not independently. Forward process alone.
yes, sure.
And hence, in that, the embedding is a joint embedding, not a individual embedding.
Yes, of course.
And there's a universal approximation based on the signal in your stochastic, not the data.
I agree. I mean, the point is like,
This could be a discussion we could have.
I'm-
I want to limit it.
I'm just saying,
You know,
we are at the stage below doing a more geometric analysis of the input-output maps, and we are having the first step done, which is the step actually doing fully adaptive or co-evolutionary limits, which is meaning we have this analogy between the discrete and the continuous world. That one we can do, but we are not beyond that yet. So don't mistake this. Like, of course, theoretical research is slow. I agree with you. You want to do this more practically and stuff, but theorists are, like me, are slow.
agreeing with what you say.
Yeah, they are. These are coupled sort of limits.
Right.
These are coupled limits. These are coupled limits. Don't worry. So.
All right. So I think we're going to stop here. We are going to close the first session. So let's thank again the speaker for this morning.